The fastest fighter jets can pull more than 9 times the force of gravity, enough to drain the blood from a pilot's brain in under 2 seconds. That's not the hard part. Building one from raw materials requires command of at least a dozen separate industries at once, and most nations on Earth can't manage even half of them. Strip everything away and the challenge scales to the size of a civilization. What a fighter jet actually is metal moving fast enough to generate its own shock waves, wrapped around a controlled explosion the size of a school bus, guided by computers faster than human reflex, and made invisible to the sensors built to kill it. Each of those is a separate wall. None of them stand in a row. They're stacked. Rebuilding attempts almost always start with the airframe, and almost always collapse there first. Early military aircraft were wood and canvas. They burned. Aluminum came next, cheap and light, and it built every propeller-driven fighter of the 1930s and 40s. Push it past around 300 degrees Fahrenheit, and the crystal structure begins to weaken. Supersonic flight generates exactly that heat from air friction alone. Titanium solved it. The SR-71 Blackbird, the fastest manned air-breathing jet ever flown, was more than 85% titanium by structure. Getting titanium to flight tolerances fights every cutting tool that touches it, and developing the required machining infrastructure took decades. Carbon fiber composites came next, roughly 40% lighter than steel at comparable strength, used throughout fighters like the F-22. Aerospace-grade material isn't chemistry you master in a year, and a small deviation in the curing oven causes the layers to delaminate invisibly until the aircraft doesn't return. Weight is the enemy. Every added kilogram demands more thrust, more fuel, more structure to carry that fuel. Engineers call it the weight spiral, and it has killed programs that looked solid on paper. Crossing into engine design is where the rebuild goes from difficult to genuinely staggering. Propeller planes work by spinning blades through air, centuries of refinement, conceptually within reach. Jets work entirely differently. One of these engines compresses incoming air to dozens of times atmospheric pressure, mixes it with fuel, ignites it, then uses the expanding exhaust to both push the aircraft forward and spin the very compressor feeding its own intake. It is burning itself to run, a controlled loop, at temperatures inside the combustion chamber that exceed the melting point of the metal surrounding them. That is not a metaphor. Inside a modern fighter engine, gas temperatures exceed 1700 degrees Celsius, above the melting point of the nickel superalloy turbine blades themselves, which survive only because of hollow internal cooling channels and a ceramic thermal barrier coating applied at tolerances measured in thousandths of a millimeter. Growing those crystals in the correct orientation, a process called directional solidification, took decades to understand and another decade to industrialize. Get the blade wrong and the engine destroys itself. That solves heat, barely. It doesn't solve the compressor. Stacked in precise aerodynamic sequence, the compressor fan blades must each feed the next stage at exactly the right pressure ratio. Tune one stage wrong and airflow reverses suddenly, loud enough to be mistaken for a weapons hit, and the engine may flame out at altitude. Teams working through the 1940s and 50s burned through hundreds of prototypes before they got the compressor right. Assume the airframe holds. Assume the engine runs. Radar can still see it from 200 miles away. Stealth isn't a coating. Geometry does most of the work. Every surface angle, every panel edge, every intake position engineered from the first sketch to deflect radar energy away from the transmitter rather than back toward it. The F-117, the first operational stealth aircraft, fielded in 1983, had its distinctive faceted shape because the software of the era couldn't model smooth curves with enough accuracy to predict radar returns. By the time smooth curves became computationally viable, engineers had found they performed even better. Radar-absorbent materials do the rest, trapping incoming waves and converting them to heat, but bonding that material to an airframe and making it survive rain and temperature cycling at altitude without peeling took years of failure that nobody discussed. Beneath the skin avionics, flight control computers run thousands of corrections per second because these aircraft are aerodynamically unstable by design, more maneuverable than any stable plane can be, entirely dependent on their software to stay airborne. Cut the power and the plane doesn't glide, just falls. Here's the comparison that resets the scale. Building a propeller aircraft from scratch is a problem of manufacturing and metallurgy. Hard, achievable, something a nation with serious industrial capacity can do. Fighter jets belong to a different category entirely. Mastering this requires simultaneous command of turbine metallurgy, computational fluid dynamics, radar physics, electronic warfare, fly-by-wire software, composite fabrication, and precision manufacturing, all interdependent, all held to tolerances that didn't exist as concepts a century ago. You can't see whether a compressor blade is within tolerance, not with the naked eye, not with any casual instrument. Parts that look correct can fail under flight load in ways nothing on the ground predicted. Specialized metrology equipment does that work, and it requires its own supply chain, its own expertise, its own trained workforce. Engineers who know how to grow turbine crystal structures learned from engineers who worked it out, by destroying hundreds of test components. And that chain of knowledge has to be maintained across generations, or it's gone. Lose the factory and you can rebuild it. Lose the people and their records and you're starting over from experimental failure. Lockheed Martin alone employs over 100,000 people. For the F-35 program alone, more than 1,500 suppliers across multiple countries contribute components. One nation going it alone isn't rebuilding a jet. It's bootstrapping an industrial civilization from scratch. There's no shortcut into that list, and no single factory that produces it. Fewer than 5 countries on Earth can design and domestically manufacture a modern fighter: the United States, Russia, China, and arguably France, with lingering questions around engine technology even there. Nations with advanced economies and world-class universities, Japan, South Korea, most of Europe, still rely on foreign engine cores or avionics for their most capable platforms. Speed is the last thing that matters here. Fighter jets are a measurement, a way of asking how many rungs of the industrial ladder a civilization has actually climbed. Go back to the stripped-down premise: no factories, no supply chains, no institutions, no trained workforce. Rebuilding a fighter jet from that baseline means rebuilding an entire civilization first. Its construction is just the final step. And even then, the first one might not fly.